Okay, so we want to start by finishing page 317, number 30. And we had an oddly shaped tank. And we had 0, 1, 2, 3, 4, 5, 6. And for each of these heights, you had values in the book. And remember that what we were really trying to do was here was the tank and there was some length that went back, and we were trying to figure out what that length was. And we said that we could find the volume of that tank by taking the area of this part here and multiplying it by the length. It was a little further complicated because what we really knew was the amount of mass that we needed. So we knew, the amount of weight that we needed. We knew that we needed a weight of 5,000 pounds of fuel to go into there. And somebody said that we could take that density, which was equal to weight divided by volume. We know what the density is, we know what the weight is, we can calculate the volume, and then use this equation to again to figure out what the length was going to be. Okay? So that kind of sums up what we talked about yesterday, but I don't remember exactly where we are. Did we figure out the weight? Did we figure out the area? Okay, then did we figure out the volume? Okay, so we were working on the cross-sectional area. All right, then let us continue to work on the cross-sectional area. And what were we going to use for the cross-sectional area? Okay. And what's h going to be? H is 1. All right, because they told us that the horizontal spacing, that space between the y values was 1 foot. So we can substitute all our values in here, and you can do that too. I'm going to leave off the feet. And then what do we get using Simpson's rule for that area? Question or answer, Maddie? Hang on one sec. Let's let everybody's fast fingers go, and then I will let you give your answer. All right, Maddie, what'd you get? And what do you think our units should be? Stupid though they are. Yeah, it should be feet squared. Each of these values had a unit of feet, and then that 1 for the h had a unit of feet too. So is she right? Okay. So that's helpful, because remember that what we're really dealing with here is that V is going to be that cross-sectional area, which we just figured out, times L, but I still need to know what V is, correct? So how am I going to figure out V? We know the density. Okay, so we had that equation that isn't quite density because it's weight per unit volume, but we're going to call it density anyway. So what's my volume equal to as an equation here? Yeah, but using this equation here, because I can't use the area times length thing. That's what I'm going to substitute into to find length. So just solve this equation for volume. Yeah, but I want you to solve it for V. So, yeah. Okay. So the weight we decided, did I keep saying weight and what I wrote was V? Was that the problem? No? Okay, just asking. I know I misspeak. We were doing math facts this morning and Leo kept saying 42 and I kept saying no. He's like, I thought that's what you said 6 times 7 was. Oh, I meant to say 6 times 8. And so sometimes I misspeak. And it was snowing. It wasn't entirely my fault. But, all right, so what's the density here, the so-called ersatz density? What is it, 42? What? I know. Pounds per cubic feet? Okay. So what's the volume that we're going to need? Cubic feet. Is Priya right? Sarah agrees. Let's see what Sarah says. Okay. So now we can take this formula, the other formula for volume. So we know that volume is going to be area times the length, or the length is going to be the volume divided by the area. So we've got 119 cubic feet divided by, what did Maddie say, 11.2 feet squared. So maybe 10.63. I could see 4 sig figs. Is Zoe right? Yeah? Okay. All right, we good? We got it? All right. Are there journal questions from 6.5? Sorry. Anybody who has access to their journal have questions? I can wait if you're still copying this stuff. The exploration. Which exploration? Do we need to go through it? Was it something you were supposed to do on the journal? Okay. So did you have specific questions, Sarah? Okay, so maybe we can just kind of talk about it without doing the whole thing. So we're talking about a figure that's part of a parabola. So maybe not quite like that. Let's just make a parabola and then we'll cut it off there and there. Okay, and so then there's this area that's under the parameter or under the parabolic arch. And so this is left, middle, and right. This side is little l, this side is little m, this side is little r, and those are equal and they're both h. So it says that the area of that, so this is exploration 1, the area of that is h over 3l plus 4m plus r. And then what we're supposed to do, I think basically what we're supposed to do is show that this is Simpson's equation. And so what you need to do is, if you're going to use Simpson's equation, you have to have a function. So your function is going to be y is ax squared plus bx plus c. And if we let these be our axes, so this is 0, this is negative h, this is h, r is then y of h, m is y of 0, and little l is y of negative h, right? And you can substitute that in. And get what those values are. And that's not that hard, right? R is going to be AH squared plus BH plus C. Little m is going to be C. Little l is going to be AH squared minus BH plus C. And then I think they just want you to add it all together. So is that enough to get you started, Sarah? Is everybody else started enough on that? Okay. All right, any other journal questions? You can always come and find me later once you have access to your files. Okay, do you have anything there, Zoe? Okay. Priya, what did you say? Yeah, we're going to start 7.1. Okay, so remember that this homework is due, I believe, tomorrow. Okay, but you should have been able to do it all. Okay. All right. Just waiting for everybody to write down what they need. Okay. All right, everybody good? All right, then let's start section 7.1. Which is about slope fields and Euler's method. And Euler's method is another approximation method that we'll talk about. But this section begins by talking about differential equations, which is something that we're going to talk about in a lot more detail after the AP exam, as I've always done, because I've always had juniors in here. This is the first year in forever that I haven't had juniors in AP Calc. Usually they're transfer students. So like when Sihao and Kelly were here, they started as juniors in AP Calc with me because they'd already taken everything else. What? Yeah, Lisa, because she was ahead. Shirley took it the first year, and Shirley was a godsend because it was the first year I ever taught it. And I'd do something, and I'd go, and all of a sudden it wouldn't look right. And I'd look at Shirley, and she'd be like, "It's okay, God. Like I can see 8 steps ahead, and you're gonna be fine." And I couldn't have taught that class without Shirley. It was a godsend. That's all I can say. I thank my lucky stars that she was there. And when I had it wrong, she'd be like, "No, no, no, that's a 4. Just make it a 4, and it'll be okay." Okay, sounds good. All right, so differential equations may sound scary, but they're really not. So let's start with a common physics equation that everybody should remember from taking freshman physics with Mrs. Leas. I know not almost everybody did. Maggie, are you the only one who didn't take freshman physics? Okay. Oh, Alf, you didn't come. Okay. Well, guys will pick it. You guys, some of you had freshman physics with me, but we certainly used that equation. All right. So for the sake of Maggie and Alf, let's explain what all these things are, what all these terms are, okay? Although they are both very smart and really quick on the uptake, so I'm sure it'll be fine. So what is V? Not just velocity, but let's say it's your current velocity or speed. Because it's really V of t, we just get lazy in physics and never write it that way. Okay? As opposed to V0, which is what? My initial velocity or speed. And what's A? The acceleration. In this case, yes, which we're going to get to and how we're going to turn this into a differential equation. And then what's t? It's your current time. At which I'm measuring my v. Okay. That's why they have cases. All right? So everybody got it? Not that hard? So as Zoe pointed out, we can also write A as dv dt. And when I'm talking about slope fields, I'm often going to solve this for dv dt. So I'm going to bring my v0 over to the other side. I'm going to have divide by t and have t to the -1 and get something that looks like this, where I have my differential and then I have variables on the other side that are going to be affected by the choices that I make. So the point of this was just to show you that differential equations are something that you've come across before. They just weren't called that. But that doesn't make them scary just because we've given them a name now. All right. So you did numbers 1, 13, and 15 in your journal and found solutions to differential equations. Do we need to go over any of those? Because I'm assuming that you know how to do them. I think you're supposed to find the original formula. And you couldn't do it? Mm-hmm. So do we need to look at the first one? Well, the second and the third one don't have trig functions in them. 13 and 15 don't have trig functions. No, 13 is du dx is 7x to the 6th minus 3x squared plus 5. Does anybody else want to see 1, 13, or 15? We okay? Because we're going to do an example. We're going to go ahead and do number 18, which will bring a lot of those things together. Did we do the journal? Did you guys do the journal and do the problems? If I checked your journals, okay. I don't care, but it affects how I teach if you haven't done your part. So, who read the section? Okay. And if you read the section, did you do the journal too? Kind of, sort of. Okay, so it's like half and half. So the half of you that didn't, life happens, okay? Nobody next year in college is going to breathe down your neck because you didn't do what you were supposed to do before you went to class. You may choose not to go to class, okay? No, it's really not, because you have to make the material up. But, you know, just if you have issues once you go through it, come and find me, okay? And that always stands for everybody. All right, so let's do number 18. And we'll try to fill in some more details here to help those of us who are going into this blind, which is fine. I know. I didn't have time because I was messing around with the projector. So, 11 through 20 says solve the initial value problem explicitly. So for number 18, we have dx dt is 1 over t minus 1 over t squared plus 6. And if we just took the antiderivative of this, we would have to put that plus c, because it would be the general solution, which I usually like to think of as a family of solutions. And we've talked about this, or at least we've mentioned it once or twice. So just to kind of review what we've talked about before, if the derivative was 6, okay, what's the antiderivative of 6 going to be? 6x. Hang on for a minute, okay, which is a what? What shape is the curve? A line. That's okay. All right, so it's a line. And what's the derivative again? What does derivative mean? Slope of the tangent to the line. Okay, so in this case, it's going to be the slope of the line. Well, I could draw a line that looks like this, or a line that looks like this, or like this, or like this, or like this. And all of those lines have a derivative that's equal to 6. So that's why we write the plus c. Because what c does is c picks out which one of those solutions I'm going to use. So the general solution, which is this, is often called, especially when we get into the differential equations part, it's often called a family of solutions. Because I could pick any one of these lines and take the derivative and get the same answer. So they tend to be parallel, concentric, because it would be the same thing if I had parabola, if I had sine functions, no matter what I have. So this is a general solution. It's a family of solutions. And sometimes the way that I can pick out the particular and I use that word technically, the particular solution that I want is by giving you a point. And if I give you a point up here, then you know that I want this solution because it goes through that point. Okay? So to go back to the problem that we were doing, they not only give me that information, they also tell me that x is equal to 0 when t is equal to 1. So they're giving me a point that's going to enable me to figure out which of the family of solutions to that is the one that I actually want. Make sense? Okay? Because remember, when we take the derivative, when I take the derivative of this, I lose the constant, so it doesn't matter what it was. But having this point enables me to recover, to rediscover what that constant is. All right? We got it? We good? All right. So we're going to start by taking the antiderivative of this. And you know that I can take the antiderivative term by term. So what has a derivative of 1 over t? ln of t. Okay. You might want to write this one as t to the negative 2 because it's a power. So what's the antiderivative of t to the negative 2 going to be? T to the negative 1 over negative 1. You got to be careful. Okay, everybody with me? All right, Elf, what's the last term going to be here? What's the antiderivative of 6 going to be? 6x. And then I'm going to put that plus c. Because I would have lost that value when I took the derivative. I lost that information. And hopefully I'm going to be able to recover it. So I'm going to rewrite this because, of course, this is annoying me to no end. Sari, what did I do wrong? Yes, it should be 6t. Good call. Okay. So this is going to give me the natural log of t plus 1 over t plus 6t plus 6. And that, as I said before, is the general solution. And now we're going to find the particular solution by substituting in for our point. So it tells me that x is equal to 0 when t is equal to 1. So I just go through and I substitute in 1 everywhere that there's a t. And what's the natural log of 1? So I've got plus 1 plus 6 plus c. So what's c going to be equal to? Negative 7, right? So if I put it all together, I get x is equal to the natural log of t plus 1 over t plus 6x minus 7. But whenever you solve a differential equation, you need to think about the domain for which your answer makes sense. Can anybody think of any problems I'm going to have with that? negatives, okay? So t is going to have to be at least greater than or equal to 0. Why can't we have negatives, Sarah? Your name isn't Sarah. Is there a term up there that would be a problem if I put in like -10? Yeah, I have to have positive numbers if I have natural logs, right? Is there anything else up there that's a problem? It can't be 0. Why not, Maddie? Yeah. Okay. So this solution is only valid for t greater than 0. And you always have to ask yourself that question. Okay? So the bell is going to ring. We will continue with this tomorrow. Please try to take a chance, take the time to read and do the problems so that we can all be on the same page.